generally speaking, the greater the difference in electronegativity, the more ionic the bond is and the less covalent the bond is. A perfect covalent bond, of course, would have a difference in electronegativity of 0. Like if you have a carbon bonded to a carbon, they have exactly the same electronegativity, and so their difference would be 0. That'd be a perfect covalent bond. But be that as it may, you can quasi-predict larger differences in electronegativity when you have a metal and a non-metal versus two non-metals, for example. And so some of this content for Chapter 9 is kind of a review from the beginning of the semester. Ionic compounds typically are metal cations, non-metal anions. Covalent compounds typically involve two non-metals, and they're held together by covalent bonds. Valence electrons, for the main group representative elements, it's easy to determine how many valence electrons the element has because it's the same as the group number. And it's only the groups 1A through 8A that we even use this concept of valence electrons. The transition metals, those are numbered 1B, 2B, and so on. Those aren't necessarily thought of as valence electrons per se. Some of the transition metals form more than one ion, and there's a variety of reasons for that. In the center of the periodic table, you're filling the d orbitals, and so we don't use the concept of valence electrons in the center of the periodic table the way we do with the main group elements. So for the main group elements 1A through 8A, the number of valence electrons is the same as the group number, except for, of course, helium, which only has 2 valence electrons, but and so on. So it's easy to determine the number of valence electrons for a main group element. It's just the same as the group number, and you have a copy of the periodic table for the test. And if you're drawing a Lewis dot structure for an atom, well, if you're drawing a Lewis dot structure for an atom, the dots are the same as the number of valence electrons. And then, of course, if it's an ion, you got to figure out how many dots you need to add or take away from the valence electrons to get the charge that you're interested in. And then, of course, Lewis dot structures, even though there's exceptions to the octet rule, many thousands, if not millions, of compounds can be rationalized by essential atoms wanting an octet in their valence shell, and they do this either by gaining, losing, or sharing electrons. And if it's a molecule, then electrons are going to be shared. And so oxygen typically forms 2 covalent bonds, and that gives it an octet in its valence shell. Nitrogen typically forms 3 covalent bonds, and that gives it an octet, and so on. And so you only need to be able to understand really simple Lewis dot structures. Now, the non-polar covalent, polar covalent, and ionic bonds, there'll be a periodic table in the test that has the values, the electronegativity of the elements, and then also there'll be a sheet that has the guidelines as to the range of what's considered non-polar covalent, polar covalent, and ionic bonds. But one thing is obvious: if you have the same atom bonded to the same atom, like a carbon bonded to a carbon or a nitrogen bonded to a nitrogen, the difference in electronegativity is obviously 0, and you have a perfect covalent bond. The electrons are being shared mutually and equally. And then usually ionic bonds result when the electronegativity difference is greater than 1.8 or so. But if you have a metal and a non-metal, you suspect you're going to have an ionic bond. You can kind of confirm it. There are some ionic bonds that have a lot of covalent character. Again, if the difference in electronegativity is perhaps less than 1.8 or something. But the guidelines will be on the test for you for what constitutes nonpolar covalent, polar covalent, and ionic bonds. But don't lose sight of the fact, if it asks you which bond is a nonpolar covalent, and you see one of the answers involves the same two elements, it's probably the answer, because that's a perfect non-polar covalent bond when both atoms are the same. Formal charge, you know, the equation's up here, but you don't need, obviously it'll be on the board. You can determine the formal charge of a nonmetal atom in a molecule or polyatomic ion, just using this formula. If an atom is behaving in the typical manner, chemists just get used to looking at these things, but if you see a nitrogen with 3 bonds and a pair of electrons, a chemist knows the formal charge is 0. I mean, it's behaving, quote, typical or normal. But if you see a nitrogen that's got 4 bonds, or if you see a nitrogen that's got 2 bonds and 2 pairs of electrons, then there's suspect there that, oh, okay, that's probably not going to be a formal charge of 0. And you can always calculate it, whether it's 0 or some other value. It's just the number of valence electrons of that atom minus the number of non-bonding electrons minus 1/2 the bonding electrons. And don't forget, a covalent bond is 2 electrons, and they're shared by 2 atoms, and so that's why you multiply by 1/2. But it's easy to determine formal charge. Elements that can form an expanded octet, again, there's exceptions to the octet rule, and there are compounds and polyatomic ions that display these exceptions. Even though the octet rule, we can justify millions of molecules, there are exceptions to it. The octet rule can be expanded by some elements by utilizing the d orbitals found in the 3rd principal energy level and beyond. And so, just for the record, sulfur, phosphorus, silicon, and chlorine are examples of nonmetals that can have an expanded octet. So it's just kind of a multiple choice type question of knowing the identity of those. Sulfur, phosphorus, silicon, and silicon and chlorine nonmetals that can expand their valence shell to more than 8. Other exceptions to the octet rule, compounds of beryllium. An example is beryllium chloride, where there's 2 bonds and no non-bonded pairs. So the beryllium only has 4 electrons around it instead of an octet. Boron forms compounds that are exceptions to the octet rule, like boron trifluoride. The boron has 3 single bonds and no non-bonded pairs, so it actually has 6 electrons around it. Those are exceptions to the octet rule. And then there's 2 compounds of nitrogen and oxygen that are also, not only are they exceptions to the octet rule, they actually have an odd number of electrons. And this can be measured when there's the odd electron on the nitrogen of these compounds generates a magnetic field that's actually measurable. But nitrogen oxide and nitrogen dioxide are examples of compounds of nitrogen and oxygen that also are an exception to the octet rule. Moving on to chapter 10 here, we talked about valence shell electron pair repulsion theory, and really the basis for it's very simple. Electrons repel each other, whether they're in covalent bonds or if they're non-bonded pairs in orbitals, and this can essentially guide the shape of molecules. If you have a central atom in a molecule or polyatomic ion, its covalent bonds and non-bonded pairs want to get as far apart as possible. They repel each other, and they give rise to this variety of shapes. The only ones you really need to know about per se, the molecular geometry of methane. Does anyone remember what the molecular geometry of methane is?
SP2?
Well, the carbon is sp3 because it has 4 covalent bonds, that's true. But what is the actual shape of methane? When carbon forms 4 single bonds, what's the resulting shape of the molecule?
Tetrahedron?
Tetrahedron, good. Okay, the 4 hydrogens point to the corners of a tetrahedron. And again, there's only 3 that you have to know about of the thousands of compounds that are out there that we could describe with valence electron pair repulsion theory. For methane, both the electronic geometry and the molecular geometry are both tetrahedron because the carbon doesn't have any non-bonded pairs. Now, ammonia, NH3, the structure of the actual molecule is trigonal pyramidal. And that's because there's 3 bonds and a pair of electrons that point to the corners of a tetrahedron. But if you ignore the non-bonded pair, and I don't know if I should draw this up here, with methane, again, these are really the only 3 you kind of have to know. Methane, it has 4 bonds and no non-bonded pairs. The hydrogens point to the corners of this is a tetrahedron. For methane, both the molecular geometry and the electronic geometry are the same because it doesn't have any non-bonded pairs of electrons. They're both tetrahedron. Now with ammonia, you have a hydrogen here, here, and here, and you have a pair of electrons here. The electronic geometry of ammonia is still a tetrahedron. But if you cover the non-bonded pair and just look at the atoms, this structure of the molecule is called trigonal pyramidal. Okay? Molecular geometry, trigonal pyramidal, electronic geometry, tetrahedral. Everybody see the difference?
Yes.
And it's kind of easy because it's so simple. The name is so simple. The molecular geometry of water, you got a hydrogen here, and I'll go ahead and put the other hydrogen here, and then I'll put a pair of electrons back here, and I'll put a pair of electrons here. For water, if you look at the non-bonded pairs and the hydrogens, again, you got the tetrahedron, don't you? But if you ignore the non-bonded pairs, the molecular geometry of water is bent. That's easy to remember, isn't it? It's just right here, the molecule. Okay, everybody see that? Those are only 3 you kind of have to know of all the thousands of compounds. Valence bond theory and the hybridization of carbon. If carbon has 4 single bonds in a molecule, how is it hybridized? Anybody remember? If a carbon has 4 single bonds, if you see a carbon in any compound with 4 single bonds, it doesn't matter what it's bonded to. If it's got 4 single bonds, it's sp3 hybridized, okay? Always. What do you think it is if there's a carbon with a double bond to something and 2 single bonds? What do you think that is?
SP2.
Yeah, it's process elimination. sp2. If you have a carbon with a triple bond and a single bond,
SP?
just sp. And then if a carbon has 2 double bonds, it's also sp. sp3, sp2, sp, and sp. Those are the hybridizations, okay? What about sigma and pi bonds? Well, we'll just take carbon as an example. but it applies to other elements too. If carbon has 4 single bonds, it's got 4 sigma bonds. These are head-on, okay? If carbon has a double bond and 2 single bonds, it's got 3 sigma bonds and then 1, what's the other kind of bond we talked about?
Pi.
Pi bond, okay? Whenever you have a double bond, it's got a sigma bond and a pi bond. The sigma bond is head-on overlap. The pi bond is a result of sideways overlap of p orbitals. Okay? So you can't rotate a carbon-carbon double bond the way you can a carbon-carbon single bond. And then, if you have a carbon that says p hybridized in either of these examples, you're going to have 2 sigma bonds and 2 pi bonds. When you're looking at a triple bond, it's got 1 sigma and 2 pi bonds. Okay? Is everybody good on that? Molecular orbital theory of diatomic molecules and ions, and we're kind of keeping it simple. Even though we're only looking at diatomic molecules, the only ones we're really concerned with are elements. And we're going to talk a little bit today as we go through this review on ions, because you got to kind of think about what's going on when you have a diatomic ion versus a diatomic molecule. Because you got to either add or remove electrons to generate that ion. And you can calculate the bond order, whether it's a molecule or a diatomic ion. You just got to count the bonding electrons and anti-bonding electrons, okay? And we're going to look at some examples of that on the practice problem. So in the last here, just kind of a summary of stuff, and I don't think I mentioned a couple of these things. So you want to know these features involving bond order and molecular orbital theory. In molecular orbital theory, the number of molecular orbitals formed is equal to the number of atomic orbitals that combined. So 2 atoms are bringing their atomic orbitals over, and those atomic orbitals are forming molecular orbitals. The number of molecular orbitals is the same as the number of atomic orbitals from each atom combined. So, like 2 hydrogen atoms, well, it only has 1 electron in 1 orbital, so you bring these 2 1s orbitals together and you end up with 2 molecular orbitals. One's bonding and one's anti-bonding. 1s sigma. Okay? Just like with atomic orbitals, a molecular orbital can only hold or accommodate up to 2 electrons, and they have to have opposite spin. When electrons are added to orbitals of the same energy, the most stable arrangement is predicted by Hund's rule. In other words, we spread them out. When we have more than 1 orbital of the same energy, we spread them out before we pair them. Okay? Low energy molecular orbitals fill before the high energy. This is just the alpha-bow principle that we saw when we were filling atomic orbitals, except now we're doing the same thing for molecular orbitals. We fill from the bottom, the lowest energy molecular orbital, and work our way up. I haven't mentioned this before, so please make note of it. The greater the bond order, the stronger the bond. And the greater the bond order, the shorter the bond. And this has been bore out by experiment. So just taking a silly example, something like oxygen, if its bond order is, say, 2, and something like nitrogen, its bond order is like 3, well, the triple bond, of course, of nitrogen is stronger than the double bond of oxygen. Of course, it doesn't really have one, but also the nitrogen-nitrogen bond is shorter than the oxygen-oxygen bond. Its bond order is greater. Okay?